Oh, he smells delicious. Me want to eat him. Oh, but me got problem. Oh. Gingerbread man, me love you, gingerbread man. 'Cause you got cookie hands, oh, and cookie feet. Oh, you brown and friendly and delicious to eat. Oh, gingerbread man, me love you, gingerbread man. But fella, me not know what to do. 'Cause you a cookie and a dolly too. First me want to hug you like a best friend should. Then me want to eat you 'cause you taste so good. First me want to play with you my whole life through. But me want to put you in me tummy too. Oh, what a dilemma. Gingerbread man, me love you, gingerbread man. Me want to eat you 'cause you made of gingerbread. But no, 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 me love you so, gingerbread man. Yeah, me gonna keep you for a gingerbread friend and eat oatmeal cookie instead. Oh, yeah, that what me gonna do. On the other hand, me really hungry for cookie. Me eat them. No. Wait. Oh, look at those little raisin eyes. Look at that little smiling mouth. He not cookie. No, he nice dolly. Oh, yeah, we want to keep him. Yeah, we want to keep him. Yeah. Oh, but he smells scrumptious. Like cookie. Me eat him. No, wait. No, you cannot play with something in tummy. Oh, eat him. Oh, play with him, eat him. Oh, this internal conflict. Oh, gingerbread man. Me love you, gingerbread man. Me want to eat you, 'cause you made of gingerbread. But no. Me love you so, gingerbread man. Oh, me gonna keep you for a gingerbread friend and eat oatmeal cookie instead. Yeah. Oh, yeah. You want some cookie? Oh, no, you are a cookie. No, you're not a cookie, you're a dolly. Oh, no, here we go again. Oh, no, cookie dolly. Oh, what the hey? Oh, eat oatmeal. Hug. Eat oatmeal. Ah.
Monsieur?
Oh, yes. Well,
Now, what starts with the letter C? Cookie starts with C. Let's think of other things that starts with C. Who cares about the other things? C is for cookie. That's good enough for me. C is for cookie. That's good enough for me. C is for cookie. That's good enough for me. Oh, cookie starts with C. Oh, C is for cookie. That's good enough for me. C is for cookie. That's good enough for me. C is for cookie. That's good enough for me. Oh, cookie starts with C. Hey, you know what? A round cookie with one bite out of it looks like a C. A round donut with one bite out of it also looks like a C. But it is not as good as a cookie. Oh, the moon sometimes looks like a C, but you can't eat that. So, C is for cookie, that's good enough for me. Yeah, C is for cookie, that's good enough for me. C is for cookie, that's good enough for me. Oh, cookie starts with C. Yeah, cookie starts with C. Oh boy, cookie starts with C.
We can't hear you, Dr. Hibiki.
Can you hear me now? We'll go with this for now. Okay. Might get a little echoey in this room with this microphone, but actually, let's see here. This actually might work better. Let me know if this works in 3, 2, 1. Testing 1, 2. Can you hear me?
Yep, we can hear you.
Fantastic. This is on my lapel mic here. So fantastic. Anyway, welcome. Good morning to Optimal Control for our remote session. So today, I want to make a few announcements. You guys see the little title crawl at the bottom of the preview screen. Number one is homework 1 is now assigned. Okay, it'll be due in 2 weeks, and it will cover basically linear and quadratic programming, which we'll cover in more detail today. But basically, it's not too different than what we covered last class, where you're setting up objectives and constraints and using MATLAB solvers to solve the problem. Now, I recommend getting started on this as soon as is reasonable, because while the concepts are simple, I try to ramp them up in a way where they're increasingly challenging, which they'll require you to do a little bit more coding. If you haven't done MATLAB in a while, dust off those MATLAB skills. Or if you have MATLAB, it'll get you, if you have a lot of MATLAB experience, it'll get you thinking in the ways of making objectives and constraints. Okay. Now, you'll also note there are very specific instructions at the top of the homework assignment. All right, on how to submit the assignment. There will be a Dropbox link, which I will send to you via Canvas message sometime in the next few days. And there will also be and I will send you each an individualized code to submit your assignments for anonymized grading. Okay, so you don't have to include any identifying information on your homework, and so purely anonymized grading, and that's great. I will recommend that keep a copy of your own homework assignment just in case there's a technical snafu. We hadn't had one in the 2 other semesters where I did this method, but just in case, keep your own copy. So I can be like, hey, there was a snafu. Which one was yours? When we're assigning the grades. All right, but that hasn't happened when we've done this in the past. Okay, and that'll be due in 2 weeks at 5 p.m. All right. So with that, also I just want to give you a little preview as to the setup we have here for remote teaching. I can see all of your faces right now. Okay, and at the same time, I can have up my MATLAB screen here. Okay, so if you want me, so if you feel like comfortable with it, you can have your camera on, and I'll be kind of peeking over. Additionally, I can still see you now too, right here. Okay, so same deal. So when I'm lecturing at this whiteboard, which apparently I need to readjust the video settings of real quick, I can still hear you. And if you ever don't hear anything, I can hear you on this. So pop in with any questions you've got. All right, good to go? Fantastic. So let me just quickly change the video settings on this board so it's less like you're staring into the sun. Real quick. All right, camera control. Go with that. Good to go? All right. So today, we want to cover linear. Oh no, I have a billion markers here. So linear and quadratic programming. All right. So we talked about programs multiple times. There are 2 other lectures so far, and there being different subtypes of programs. And some are easier to solve than others. All right? So depending, let's go with a different color here. So mathematical programs or optimization problems have multiple subcategories. These subcategories allow us to select specialized solvers to yield solutions that are yield solutions more reliably and in less computation time. Okay. That's the big picture. Okay. So the motivation is that when you have your optimization problem, what are the 3 things that we like to define? And we want to rattle them off for me?
Design variables, constraints, and cost function.
Exactly. So design variables, constraints, and your objective or cross function, or the cost function. And you can call them decision variables too. So you have a number of decision variables, okay? And normally in this class, they're going to be a subset of all real numbers, right? Okay? So a way that you could look at, so you can visualize an optimization problem as having one dimension per decision variable. So imagine you have one decision variable. We'll call it X. There's X on that axis, and on this axis you've got J of X, which is your objective function. Okay. Relatively simple optimization problem, one decision variable and some objective function. Now, if we know nothing at all about the objective function, it could be this, it could be that, nothing at all. The only way to get the best solution would be looking at all these points on the line. You have to search the whole dang thing to find that one's the best. So if you know nothing about j of x, the only way to find the best x is an exhaustive search. And you can do that. I mean, you can't do every real number, of course. You'd be there a while, but you could sample it along all those points and do a search, right? Not the worst thing in the world. It depends on how long it takes for your computer to evaluate this objective function. You try an x, you put it through the objective function, out pops an answer. Now, what we were doing last class was, which problem were we coding up last class? Which problem?
The fencing problem.
The fencing problem, right, Brandon? Thank you. And so in that time, it was a really easy thing to solve, just a multiplication, right? Now, this is an optimal control class, though. What if your objective function required you solving a computer simulation of your robot doing a thing, or a computer simulation of your, let's say you're controlling a solar panel. We were trying to see how much sunlight you got in a day. That would take a long time, right? So this can or cannot work depending on how fast your j of x is to solve. But that's not the only problem. You can also, so if you have more design variables, you increase the number of possible best solutions exponentially. So for one design variable, let's say you took 100 points along that line to try, right? Let's say you took 100 choices. If you had two design variables, all of a sudden this becomes not a line, but a plane where the objective function is up, which means we now have 100 squared choices. You can see where this becomes problematic. If you have three design variables, you have 100 cubed choices. The optimization problem that I showed you, do you remember kind of the blue robot that was walking with tennis shoes? People remember that from the first lecture? That had 10,000 design variables. Yes, okay, yeah, William Monroe, Harshcenter, don't have a heart attack, okay? I saw, don't clutch, if you're feeling palpitations, call a doctor, okay? All right, so 10,000 design variables. Clearly, we did not use this approach, right? So clearly, this does not scale well for exhaustive search. Right? This actually has a name. It's called the curse of dimensionality. Okay? Called the curse of dimensionality. Cool name. think it traces back to the 1960s, where you have more dimensions and it adds all of these you have more variables, it adds more dimensions, and that's a huger and huger problem to solve, right? If you know nothing about the objective function, but of course we do know something about the objective function in a lot of cases beforehand, hence these subcategories of problems. That makes sense? More dimensions, more problems, Luke. That's right. As many rappers have often said. Okay. All right. So I'll write that out. So, however, having knowledge about the objective function and constraints makes these problems more tractable. Okay? So here we're going to introduce the idea of convex programs and convex functions. There's a beautiful textbook, and if you go to the Canvas page, you can go to last year's Canvas schedule for last year's course, and it has links to a number of reading materials for you to peruse, roughly on schedule with what we're doing. And there's a great free textbook called Convex Optimization, for which there's a link online. It's a famous textbook in this in this field. Okay, but so it's a big concept in optimization is convexity. Okay. So in short, so you can get really formal definitions from a textbook like this, but for our applied class, a convex program has a single local optima that is the global optima. Okay? And this optima or minima, in the case of an objective function, a minima, this optima can be found by descending the objective function gradient and writing constraint lines. Okay? That's the informal way of looking at how some of these algorithms work for solving these problems. And I'll give you an example. So an example. We have our decision variable x, which is just a single real number. Single real number, easy. And we'll say j of x is equal to x squared. Further, we'll have our constraint functions. They don't exist in this problem. Okay? So let's draw out. We have our decision variable x, our objective function j of x, and that's our objective function, right? So let's pretend we're optimizing this problem. We are the optimizers, and we will start with. Do you remember what x0 was in our lecture last class when looking at the NLP solver, using the nonlinear programming solver? Remember what x0 meant?
Our initial guess.
It was an initial guess. That's right. I didn't quite see who. Oh, it was Elfieta. Thank you, Elfieta. An initial guess. Okay. Now, let's descend the gradient of j of x. Now, all of us have taken Calculus 3 at some point in our recent or distant past, where the gradient has an actual mathematical definition. So we're really talking about the gradient as being the partial derivative of j of x, where x is a decision vector, right? It's a vector with respect to your vector. Okay? Our vector happens to have just one element this time, right? But it's a partial derivative, right? In this case, just one dimension, but you can have it for multiple dimensions. If this were a paraboloid instead of a parabola, for instance, or a hyperparaboloid, right? Okay, so let's descend the gradient of j of x. Well, what is the gradient of j of x on this plot, graphically speaking? Okay, it is the tangent line of this, right? That's the partial derivative of j of x with respect to x, right? That tangent line. So we're going to descend that gradient. Okay? That means we're going to go that way. And you'll have some kind of step size in a gradient descent algorithm where it'll step more or less depending on how steep the gradient is. But we're just doing this qualitatively. So we step in that direction. We're a little closer, right? Let's descend the gradient again. Well, what's our gradient now? It's now this. So we're going to step in this direction. What's our gradient now? There it is. What's our gradient now? Until eventually you get down to 0. You might overshoot, but if you overshoot, guess what? You're coming back, right? So gradient descent yielded the global optimal solution. And because it's a convex function, it will do that for any initial guess. for any initial guess for a convex objective. A qualitative way, another qualitative way of what a convex function is it's a function with no nooks and crannies, right? So there's no nooks and crannies in this, as opposed to what if you had this? It's a nook and or a cranny. Not sure which, right there. So this would be non-convex. This is convex. So naturally, parabolas make great convex functions. Right? So a lot of times in optimizations, you'll see objective functions that are the squares of things. You know, and this is a really good reason. One of the big reasons why. Okay. So that's the general idea of a convex function. There are many, again, if you want to go into depth as to all different kinds of convex functions there are out there, I recommend the textbook Convex Optimization by Stephen Boyd. And again, it's a free textbook, and there's a link on the Canvas page in the 2021 course in the course notes. All right. This making sense so far? Trying to make this really accessible, even though you might not have had like 3 graduate courses in optimization theory, right? So you can get right to using this stuff. So this brings us to our actual classes and categories of programs. We have all this. I'll give you all a second to write this down, and I'll erase it off and start fresh. Cool. Thank you all for participating, by the way. And the aim here will be to get us programming some linear and quadratic programs and have it recorded for you all today on the computer. So, linear programming. Or LP. So, linear programs are of the form where you take the minimum, you want to find the minimum, where x is your decision vector or design vector, where you're minimizing as your objective C transpose X. ST, which always stands for subject to, whenever you see that, and after which it will describe constraints, subject to constraints. AX is less than or equal to B. right? So where x is an element of all real numbers n, meaning that there are n decision variables. And C and B are vectors. And A is a matrix. Okay. So very simple matrix algebra going on here. Again, nothing really more complicated than matrix multiplication. Okay. So if you can write it in this form, if you can write your program in this form, congratulations, it's a linear program. And LPs are convex. Okay. If there's any solution, it'll be the best solution. There won't be a better. If you find a local minima, it's the global minimum. All right? Now, why is that? Okay? So this means that this form would mean that any objective function, so an example would be of an objective function would be 2x1 plus 3x2 minus 4x3 ... as many as you want. So that's linear. Check. You can't have x1 multiplied by x2. Is that linear? No. So you cannot have, so this is my wrong x. Wrong. You can't have x1 times x2. Not linear. And also, all these constraints are linear. See that? So A is a matrix, and all these are full of constants, by the way. You can't try to smuggle in decision variables in here. They have to be constants. Make sense? Not linear. LPs are convex. So, in short, your program is linear if and only if both the objective function and constraints are linear. They both got to be linear. Okay. That's an example of an objective function that you could have. Another example could be really easy. Let's take a one-dimensional version. Your objective function could be just x1, right? Could be really easy. And the nice thing about this is that if you have a linear program, it can have thousands and thousands of variables. And because you can just go use gradient descent, because it's convex, and you end up writing constraint lines, I'll try to draw an example for you, it's super quick to solve. Like we're talking less than a millisecond for thousands of variables. With modern computing. Who's here has ever like worked with an Arduino or any little micro board processor? Any of those things? Yeah. There are linear programming solvers for those. For Arduinos. Yeah, pretty cool, right? Yeah. So why linear constraints are important? So graphically, let's say that we had two variables, x1 and x2. We had two design variables, okay? And we had a bunch of constraints that are linear, okay? And our objective function is to minimize x2. All right? As it stands, if you didn't have any constraints, minimizing x2 would be really easy. It'd be minus infinity, right? But let's add some constraints that are linear. So subject to, let's say that x2 must be greater than or equal to x1. We could write that as a linear constraint, right? We could write it in the form of the ax equals b by putting we put the x on the other side, so it's like greater than or equal to 0. We flip the sign like we did last class. We could put it in that form. Okay. So, but let's draw this graphically and see what it looks like. So x2 must be greater than or equal to x1. That means that if I had the line x2 equals x1, which is this 45-degree line, I can't be down here. Can't be beneath that line, right? Because x2 has to be greater than x1. 50, right? Okay. So if we were to try to solve this problem now, how would I do that mentally? Well, I would say I'm trying to minimize x2, so I'd go down, I hit a line, and I'd keep going. I would ride this constraint line down to minus infinity. So my best solution will be minus infinity for x1 and x2. Any questions about that? Okay, pretty simple, right? Well, let's add more constraints. Let's say that x2 must be greater than or equal to minus x1. So let's draw x2 equals minus x1. It's that line, right? And we can't be below that line. And again, let's optimize ourselves. Let's start here. We ride the constraint line down as far as we go. Boom. We're at that minimum. Let's try starting over here. Boom. Ride it down at that same minimum. Let's add another constraint. Let's say that x2 must be greater than or equal to minus 1/2 x1 plus 1. Now, depending on how good you are just graphing in your head, that means the y-intercept is going to be at 1. We'll say that's 1 right there. The slope's going to be minus 1/2, so going slightly down. So it's going to look like that, right? Can't be beneath that line either. Well, guess what? Same deal if we try to optimize this ourselves. We say we start here. Sorry. We start there. Boom. Ride this constraint line down. We hit there. We hit the bottom. Let's start over here. Boom. Ride down. Boom. Boom. Hit the bottom. Nice and convex. And it doesn't matter how many lines I add. There's nothing I can do. There's no linear constraint I can add that'll make this have a nook and a cranny. Okay? That's some intuition as to why. All right, any questions about that? Okay, well.
Dr. Hibiki, I have a question.
Yes, Hamza.
So if the final constraint that you added, it was a horizontal line, then you would have multiple minima, right?
Yep, you would. You would have multiple minima, but you would not have any better than any other one you would find.
Yeah.
That's maybe the more precise way of saying it. So if you found a minima, you're not going to find a better one anywhere else.
I see.
Okay.
Thank you.
You got it. Okay. Well, why don't we try to do this in MATLAB? Okay. Let's do it. You all still hear me okay? For MATLAB? All right. Let's do some MATLAB. Oh, this is some cool code I was running. This is something called simultaneous localization and mapping for robotics. It's for fun, but we have a little robot rolling around. But anyway, that's fun. That's for a different class, though. So let's make a new script in MATLAB. Okay. We're going to call it test lin prog.m. So take your time and pull up some MATLAB. And I will save this somewhere. Too many files. I need to be more organized. Let's see. Test lin prog. Okay. Close. This is clear. Close all. Cool. Y'all see this okay? Should the text be bigger for you? I can make the text bigger. Not really. I see some scrunched noses. I'll go a little bit bigger. Okay. Go to home. Because sometimes it gets a little distorted over the Zoom connection, the way I have this set up. So let's go under preferences, fonts, make it size 36. Cool. Hopefully that reads pretty clear. All right.
It's clear, but it's still like blurry.
Blurry. So it's being recorded locally. Okay, it's a little blurry. Can you read the text though?
Yeah.
Okay, that's okay. That's what we'll go with for now. Okay. I can see it on my backup Zoom computer. I see the slight blurriness, but I also can read the text. So, all right. So let's go with this. And if you have any questions about what's being typed, let me know. All right. So we're just going to clear CLCN clear and close all. And we're going to try to solve that linear program on the board. Okay. And we're going to solve it using linprog, or linear programming. So help linprog. Boom. Here we go. Linprog, linear programming. Attempts to solve the following linear program. F, so it says F instead of C times X, subject to AX is less than or equal to B. Okay, pretty straightforward. So what do we need to do? So what do we need? We say we need F, we need A, and we need B. Okay? So let's go back to the board and get those for us. So our objective function, j of x, is now equal to, we'll call it on the board, c of t times x, but it needs to be x2 is what it's equal to, right? So that means in order for this matrix multiplication to work, what is the size of x? Anybody? You can do it with your fingers if you don't want to unmute. What's the size? 2 by 1? 2 by 1. Thank you, Brandon, for the fingers. Applause for Brandon. Thank you. All right, I'll get that marker cap later. So x, so it's got to be a 2 by 1, right? That means that this thing that's multiplied is being multiplied by, just to make matrix multiplication work, it's got to be blank by 2. It has to be, right? So if you ever go into MATLAB and you try to multiply matrices together that don't have these at the same dimension, it'll say matrix dimensions do not agree. That's a math problem, okay? So it's got to be a blank by 2. And because j of x is a scalar or a vector, which one is it? 1 for scalar, 2 for vector. 1 for scalar, 2 for vector. 1, it's actually a scalar. It's a scalar. So that's scalar. J of x returns a scalar. That means this needs to be 1. It needs to return one number. So C transpose has to be 1 by 2, which must mean that C has to be the transpose of that. So C must be a 2 by 1 vector. So C is always the same size as X. Okay. Always the same size as X. All right, now I'm going to go searching for that marker cap. Marker cap, got it, retrieved. So C is going to be a 2 by 1. And when multiplied by X, which is a vector containing X1 and X2, needs to return X2. So C transpose is going to have the first element times X1 plus the second element times X2. So the first element should have a 0 because there is no X1 in our objective. But it does have 1 times X2 in the objective. So the second element will be 1. So 0, 1. Okay? There's a good hack if you don't want to think about this. That C is equal to the partial derivative of j of x partial x. That's your gradient. So if you remember your Calc 3, what that would mean is it would return a vector of the size x, where the first element is the partial derivative of j of x with respect to the first element. So the partial derivative of j of x, which is x2, with respect to the first element x1, the partial derivative of x2 with respect to x1 is what? Goose egg, 0. And the second element, partial derivative of x2 with respect to x2 is 1. Okay? That's the way you mathematically get your C. So maybe you don't have to think it's quite the same way. Does that make sense? Okay. So let's try and solve that problem without the constraints in MATLAB. So back to here. So if we wanted to use linprog, and we'll save x, the x is equal to linprog, and we'll give it our f vector, which is 0, semicolon 1. Let's see what happens when we don't give it an a and a b. Let's see what it tries to do. See if it will give us an answer. Okay. Problem's unbounded. It didn't like that. I guess it was going to go, it went down to negative infinity. It's like, what are you doing to me, Dr. Hubicki? So.
I have a question real quick.
Yeah, what's up, Brandon?
Is the F the same thing as the C we just found? C transpose?
Yes, it's exactly the same thing as the C we just found. MATLAB calls it F. Some textbooks call it C. Tomato, tomato. Good question, Brandon. So, so that's why I put in the exact same value here. All right. So, clearly not enough to solve. It's unbounded, means it's going to go down to negative infinity, just like we said. Some solvers will actually tell you the answer is negative infinity. So, all right. I'll let that go, and then go back to the board. Oh, this is cool. Okay, all right. So now we need the constraints, right? How are we doing on time? Okay. Now with the constraints, we need them of the form ax is equal to b. Now a is of size number of constraints by number of decision variables, and b is number of constraints by 1.
Professor, I have a question.
Yeah, what's up? I believe that's Tanner in my brain.
Yes, yes,
okay,
it is.
Okay.
So is there a way to simplify this, because we know that x2 is greater than or equal to negative x1 is technically not necessary for that.
Greater than or equal to minus 1?
Because you're going to get the same answer if that constraint isn't there.
Is that true? I'm not sure. Oh, I see. I see what you're talking about. The same optima. There are advanced ways to get rid of constraints that might be unnecessary.
Yeah.
But computationally speaking, like it doesn't make much of a difference to the problem you're trying to solve for this linear thing. Yep. Is there a way? There are almost certainly ways to mathematically deduce which constraints are unnecessary for the given objective. That's a little more advanced and frankly unnecessary for what we need to do.
Okay. Yep.
Great. I see what you're saying. Thanks, Tanner. So now we have these other constraints, and we need them to be of the form ax is less than or equal to b. Sorry, ax equals b. It should be less than or equal to b. Thank you. And so we need them to be, so we're going to take our first constraint, which is x2 is greater than or equal to x1. And what we're going to do is going to put x1 on the other side. You can have minus x1 plus x2. It's helpful to have them in the order of decision variables. They'll make your life slightly easier when you're coming up with these constants. Obviously, that's greater than or equal to. Flip the sign. We take the negative of everything. So we get x1 minus x2 is less than or equal to 0. That's our first constraint. Then we have our second constraint, which is x2, is greater than or equal to minus x1. Put it on the other side, you get x1 plus x2 is greater than or equal to 0. Greater than, got to flip the sign. So it gives us minus x1 minus x2 is less than or equal to 0 for our second constraint. I believe in your algebra skills. Okay. And finally, number 3, we've got x2 is greater than or equal to minus x1 1 half x1 plus 1. We want our constants on the right side and all our variables on the left side. So we're going to put that on the other side. We're going to get 1 half x1 plus x2 is greater than or equal to 1. Flip the sign, we get minus 1 half x1 minus x2 is less than or equal to minus 1. Because we have all 3 of our constraint functions here, all in the order of the variables that we have, okay, our A is going to be very easy to fill in the entries. So our first coefficient is 1, then minus 1, 1, minus 1, minus 1, minus 1, minus 1 half, minus 1. And B is all these constants on the right-hand side, 0, 0, minus 1. Any questions about that? Now, just like there was a nice mathematical trick to coming up with a C vector using a gradient, there's a similar trick with the A matrix. And what you do is you put all of your functions on the left, all of your variables on the left side, and then you take something called the Jacobian. Who here has heard of a Jacobian before? Yeah, people have heard of Jacobian. Yeah, well, some of you have it. Believe it or not, it's not nearly as fancy. It's not nearly as complicated as it sounds to generate one. But you can do cool stuff with them. But the Jacobian is just, instead of taking the derivative of a scalar with respect to a vector, which was called the gradient, the Jacobian is the derivative of a vector with respect to another vector. And that gives you a matrix, like this matrix. All right, so let's go back to the board, go to the computer. Okay, so we defined F. Let's put it in its own line of code here, just to make it a little cleaner. So 0, semicolon 1. Now we're going to define A, which according to my board was 1, minus 1, minus 1, minus 1, minus 0.5, minus 1. And our B was 0, semicolon, 0, semicolon, minus 1. Then our linprog just becomes F, A, and B. Boom. 2/3, 2/3, which, if you remember my little mental, that diagram I drew, that's about where it was on the x1, y1, sorry, the x1, x2 coordinate. Okay, that's linear programming. Okay, now we have about 15 minutes left. I want, because the next thing I want to cover is quadratic programming. But at this, so at the same time, I feel like I want to define a Jacobian for you all. just so you know what it is, and you can do this more systematically. So let's do that at the board really quick. So while a gradient is the partial derivative of a scalar with respect to a vector, which gives you a vector. Where we'll say the scalar is a 1 by 1, and this vector is an n by 1. The vector it gives you is an n by 1. Whereas a Jacobian, and I'll write it out as so the partial derivative of f with respect to x, which is a vector consisting of x has x1, x2, xn as a vector. This is just me writing it horizontally with a transpose on it for stating whiteboard space. That's all that is. The Jacobian is the partial derivative of a vector. We'll say it's m by 1, m as in magnificent. With the with respect to another vector, n by 1, as in not so magnificent. And it gives you a matrix, which is m by n. So partial f with respect to x, where now f is also a vector, consisting of f1, f2, fn, fm, as in magnificent, and x is x1, x2, xn, as in not so magnificent. Okay. So it's a vector. Okay. So partial f, partial x is a matrix with partial f1, partial x1, partial f2, f1, partial x2, partial f1, partial xn. Next row, partial f2, partial x1, partial f2, partial x2, partial f2, partial xn. Then you have lots of dots going down. You fill it in until you get the partial fm, partial x1, partial fm, partial x2, partial fm, partial xn. See the pattern? 1, 1, 1, 2, 2, MMM, 1, 1, 1, 2, 2, 2, and then. So you can see how that might get tedious, even doing it for large vectors. MATLAB actually has a function that we won't that's good for checking Jacobians. Anyone want to guess what it's called? Anybody?
Jacob.
Yeah, it's actually a full word, Jacobian. Close. Jacob's close.
Nice.
Jacob's here in this classroom, but no, but Jacobian. It actually is Jacobian. All right. You have to know how to use the symbolic toolbox to use that, and we will cover that. Okay. But the A matrix is just the Jacobian of your constraint functions with respect to your design variables. F1 would be your constraint function, everything on the left side. F2 is the same thing for your second constraint, etc. So I wanted to just demystify Jacobians, because I remember being scared of that word when I first heard it. It was being bandied around as if I was supposed to know what it was. Okay. Now that's not to say there aren't entire graduate courses that you can take that will tell you all the crazy things you could do with Jacobians in all kinds of fields, right? But this is how you calculate it. All right? More than just optimization, all kinds of fields. All right, any questions there? And you can see how, if your problem is linear, you have linear constraints, all those partial derivatives, they return constants. If they're not linear, all of a sudden there's going to be non-constants in there. That'll be a hint that you're doing something wrong, and it's not a linear constraint. Okay. All right, next. Well, we'll finish up a bit with quadratic programs in the last 7 minutes we've got. So, quadratic programs. Or QPs. Super popular these days in robotics, especially in robotics and other fields. So much in robotics is like, I would say a good fraction of the papers I'm reading are, how do we turn this robotics problem into a QP? Once it's a QP, oh, we give it to a QP solver, and it's gonna solve it for us. We consider it solved, right? Okay. There are a few more conditions on QPs on whether or not it's convex, but a QP, quadratic program, a QP takes the form where you minimize x. So you're minimizing the objective function with the design vector x, with the objective function of 1/2 x transpose times q times x plus C transpose times x. Subject to the constraints, AX is less than or equal to B. So for it to be a quadratic program, the objective function must be quadratic, meaning it'll have terms like, oh, x1 squared, or even x2 times x3. You know, not x1 cubed or x1 times x2 squared. So there should only be, at most, 2 design variables multiplied together. Okay, then it's quadratic, but the constraints still need to be linear. Okay. There's a temptation for people learning this. They'll say, in a quadratic program, both the objective and constraints could be quadratic. No. That's something else. It's called a quadratically constrained quadratic program. It's a different thing, a QCQP. All right. This is a QP has a quadratic objective and linear constraints. Very important. Okay? That's a quadratic program. So if Q is positive, definite, then the QP is convex. Okay? Now, people who have not taken linear algebra, positive definite is just saying, oh, that the matrix is greater than 0. And what that specifically means is that the eigenvalues of this matrix are all greater than 0. Okay? You don't need to know how to compute eigenvalues by hand for this class. There are eigenvalues functions in MATLAB. I'll show you real quick. So all eigenvalues are positive, and the MATLAB, so if you want to check it in MATLAB, the command is eig. Okay. And really what that is doing, in effect, by saying that this must be positive, it's more or less saying that the parabola or the paraboloid that you're making is curving up. The bowl is up, which means you would go down to the bottom of that bowl. Okay? Whereas if it's not, it's upside down. It could be upside down, at which point it can go off in that direction, or it could go off in that direction. So you can have two or multiple like local minima, right? So that's what this is sort of checking, is that whether the bowl of the parabola is up or down for the objective function. That way, when you want to minimize it, you can hit the bottom, right? So we have like 1 minute left. So Q is a matrix. You know, X is an element of all real numbers n, and the Q must be n by n. So it's a square matrix of the same with the same number of rows as your design vector. And the same rules for A, X, and B. That's the same as for linear programs. All right? So the quick trick for a Q is often called the Hessian matrix. So if you take the Hessian, which is a lot like the Jacobian, all right, of your objective function, it'll get you Q. In fact, some textbooks and even MATLAB will call this matrix H for Hessian. This one calls it Q for quadratic. And CT, same deal. You have your gradients. All right. We're at time today. We've covered linear programming in some detail. I think enough detail for you to do all the linear programming questions for your homework. This is, I think, a good start for quadratic programming, where you'll use quad-prog in MATLAB. Any questions for me at this stage? Yes, Ella.
Could you show your MATLAB? Mine is giving me the wrong numbers.
Sure, I'll pull it up. There you go.
Thank you.
Leave that up. Cool. So that's the end of lectures for today. So feel free to go about your merry days. And anyone who has any questions, I'll be here for a few minutes.
Thank you.
You got it.
Thank you.
You got it, Grace. Thanks so much.
Dr. Hibiki, for the project, could I just do something like an inverted pendulum, just like a simulation, or even actually making it? Would that fulfill the requirement for the project?
Yeah, I think that it would. Depends on what you want to do with it, and I think that's what when I get the project. So that's a fine project idea. The question is what methods will we use to control it, and certainly I think that what you want to do. Sorry, what was I going to say? So like if you want, we would certainly be doing trajectory optimization. I think is one option. And the other is something called model predictive control. I think that that's a good one for using for the pendulum. Okay.
Okay.
If you want to get a head start on what those are, all the lectures are up from last class, so you can sort of pick out a few of those if you want to get a preview. Or
Okay.
when I establish office hours, you come by office hours and ask a question about that. Okay.
Thank you very much. Appreciate
You
it.
got it, Austin.
I also
Ella,
have a question
yeah,
regarding
Matthew, what's
the
up?
project.
Yeah.
Have you decided or thought about on the regarding the groups for graduate students compared to undergraduate?
So I think that graduate students are going to have definitely smaller groups. I would say a maximum 2. Okay. For a project. Are you looking to have any graduate students in your group? Are you a graduate student for this class?
Yeah.
You're a graduate student for this class. So I don't have a firm decision. I'll leave it at that, so I don't mislead you. But it won't be a group of 4 for you.
So if it is,
Yeah.
so I mean, regardless, it could be a group of like maximum 2, or it could be on your own, but not like
Yeah.
specifically only on our own right now.
Yeah, on your own is definitely an option, but not specifically on your own right now. So if you have a partner in mind, I'll consider that. Okay?
Okay, sounds good. Thank you.
You got it. You got it. Ella, any luck with that?
No, I don't know why it's giving me 0.9524.
I'll tell you what. I'll stop recording now, and you can pull up your screen. Okay?